Alright, welcome back everybody. In this video we're going to continue talking about section 6.2 of AP Calculus, Approximating Areas with Riemann Sums. This is part 2, the first video of part 2, hopefully the only video of part 2, as long as I can keep myself from babbling here. Alright, so in the last lesson, in part 1 of Approximating Areas with Riemann Sums, we found the values of the Riemann sums for equations. And reality of it is that we're going to have better methods for finding the definite integral or the area under a curve when we know the equation for a function. When the Riemann sum and trapezoidal rule are most important for us is when we're working with tables of numerical data. Because in those situations, they are definitely the best option that we have to approximate the area under the curve described by the data. These are also problems that show up in the AP exam with great frequency. So what we're going to do is we're going to look at a few examples that have shown up on past AP Calculus exams related to using Riemann sums or the trapezoidal rule. And we're going to just go through a couple examples of those. And then we're going to be done. All right, let's start with the first example. This comes from free response question number 1, which is a calculator question from the 2017 AP Calculus exam. It says a tank has a height of 10 feet. The area of the horizontal cross-section of the tank at height h feet is given by the function a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values for a of h are given in the table below. And in part A of this question, we're going to use a left Riemann sum with the 3 subintervals indicated by the data in the table to approximate the volume of the tank. Now, one of the things you've got to be aware of when we're doing these, unlike in the last video where we were using equations and we always used uniform widths for our rectangles, when we're looking at tables of data, we really have to pay attention to the widths of the rectangles because chances are they're probably not going to be uniform. Every now and then they are, but chances are they won't be. So I'm going to first use a left Riemann sum to approximate the volume of the tank, because volume is the accumulation of the cross-sectional area. All right, so we're using a left Riemann sum, which means for each subinterval we want to use the left endpoint. All right, so I start with the first subinterval, the interval from 0 to 2. The width of that rectangle is going to be 2, and the height is going to be from the left endpoint of the interval. The left endpoint of the interval from 0 to 2 is at 0, and the function value there is 50.3. Next subinterval, the subinterval from 2 to 5. The width of that subinterval is 3, and for the height we're going to use the value of the function at the left endpoint of that interval, which is at 2. And that value is 14.4. And then for the last subinterval, the width of the subinterval is 5. And for the height, we're going to use the left endpoint, that's 6.5. And so now all I need to do is go ahead and calculate this, and this is a calculator problem, so I'm going to go ahead and just break out my calculator. And so I've got 2 times 50.3 plus 3 times 14.4 and 5 times 6.5. And I get 176.3. Now since the height is in feet and the area is in square feet, the volume here is going to be in cubic feet. So there's my answer. All right, part B. Does the approximation in part A overestimate or underestimate the volume of the tank? Explain your reasoning. Okay. Well, we're told back here in the stem that the function A decreases. So this is a decreasing function. Okay, and if you think about it, when we have a decreasing function, the left endpoint of each interval is going to be the highest. And so the approximation is an overestimate. Because a of h is a decreasing function. So a left Riemann sum will overestimate because the approximation values are the largest value of the function on each subinterval. I don't think I have to write this much, but I got a little wordy here. I think you can probably get away with saying that it's an overestimate because the function's decreasing and you're using a left Riemann sum. All right, let's go on to the next one. Example 2 from free response question number 2. This is again a calculator question from the 2019 AP Calculus exam. The velocity of a particle p moving along the x-axis is given by the differentiable function v of p, v sub p, where v sub p of t is measured in meters per hour and t is measured in hours. Selected values of v sub p of t are shown in the table below, and you see the table. This is part B of that question. Use the trapezoidal sum with the three subintervals 0 to 0.3, 0.3 to 1.7, and 1.7 to 2.8 to approximate the value of the integral from 0 to 2.8 of v sub p of t. Okay, so the first trapezoid, my width is 0.3 because that's the difference between the left endpoint and the right endpoint. So I'm going to have 1/2 times the height of my trapezoid times the sum of the bases, which for the first trapezoid is 0 and 55. Notice I can't do what I did when we were doing these algebraically and factor out the widths because all of the widths are going to be different. So I have to actually calculate the value of the area of each trapezoid individually. So there's 1/2 base times the sum of those heights. And then 1/2 times, and that distance is 1.1, and then the sum of those. And since this is a calculator section, I'm going to go ahead and punch this up on my calculator. I've got 1/2 times 0.3 times 55 plus 1/2 times 1.4 times 26 plus 1/2 times 1.1 times 26, and we get 40.75. Now since the velocity is measured in meters per hour and time is measured in hours, we multiply those two units together to get that this is 40.75, and that is the displacement of the particle. That's what that represents, but we'll talk about that more later on in the course. All right, example 3 from free response question number 1, which was a calculator question from the 2021 AP Calculus exam. The density of a bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f, where f of r is measured in milligrams per square centimeter. Values of f of r for selected values of r are given in the table below. You see the table. And in this case, we don't just have, the integral from 0 to 4 of f of r dr. We've got a bunch of other stuff in our calculation here. We've got, an r inside of our integral, and we also have this constant 2 pi out in front. So we're going to have to utilize those in there. It says to approximate the value of 2 pi integrals from 0 to 4 of r f of r dr using a right Riemann sum with the 4 subintervals indicated by the data. Okay, so let's go ahead and we'll start this up. We've got 2 pi, and now we're going to use a right Riemann sum to represent this first subinterval. We want the width of the subinterval, which is 1, and then we're going to multiply that by r f of r. Okay? But we're using r f of r at the right endpoint of this interval, so that's right here. So the r value there is 1, and the f of r value there is 2. All right, next one, the subinterval from 1 to 2 has a width of 1. The r value at the right endpoint is 2. The f of r value at the right endpoint is 6. Next interval, from 2 to 2.5, the width is 0.5. The r value is 2.5 at the right endpoint, and the f of r value is 10. And then the last subinterval, the width of the subinterval is 1.5, and the r value is 4, and the f of r value is 18. And so I'm going to go ahead and calculate everything that's in here. I have my calculator set to auto mode, so I'm hoping that it's going to give me the answer in terms of pi. But we'll see. I've got 2 pi. Certainly a decimal is acceptable. This is a calculator question. 1 times 1 times 2 plus 1 times 2 times 6 plus 0.5 times 2.5 times 10 plus 1.5 times 4 times 18. Ooh, and I got a decimal. 845.088. 845.088. And my unit of measure here is what? Milligrams? Total mass in milligrams. Yeah, they gave us the unit in the question even. So, all right, there's my approximation. Is the approximation found in part B an overestimate or underestimate of the total mass of the bacteria? It's an overestimate. We're told in the stem of the problem, and we can see from the table, that this is an increasing function, and we're using a right Riemann sum. Overestimate, the function is increasing, so a right Riemann sum will always use the largest value of the function on any subinterval. All right, that takes us to the end of this video and the end of the lesson and the end of the section. So come back and join us in the future for section 6.3 when we talk about Riemann sums, summation notation, and definite integral notation. That's one of, in my opinion, one of the harder steps for a lot of students to do. So I look forward to that section. All right, have a great rest of your day, everybody, and we'll see you next time.